Hello everyone, in this video I will be explaining the mechanism of nucleophilic substitution reaction in haloalkanes. Now the nucleophilic substitution reaction in halogen derivatives containing carbon to halogen bond can occur by two mechanisms. The first one we will see here is the SN1 nucleophilic substitution reaction, or it is known as is SN2 biomolecular nucleophilic substitution reaction, and the second one we'll be having SN1, that is your unimolecular substitution reaction. Therefore, in haloalkanes we will be studying two types of nucleophilic substitution reaction, that is SN2 biomolecular substitution reaction and substitution nucleophilic unimolecular SN1 reaction. Now, in the nucleophilic substitution reaction, we know that nucleophiles, they are nucleus-loving or electron-donating species. Nucleophiles may be neutral molecules or them with a lone pair of electrons or negatively charged. Now, therefore, to study the mechanism of the nucleophilic substitution reaction in haloalkanes, let's move on with our first one, that is the biomolecular substitution reaction known as SN2 mechanism. Now, let's study SN2 mechanism. Now, in SN2 mechanism, in this mechanism, then our nucleophile attacks the partially positive carbon atom attached. Now let me write here, if we have here our haloalkanes, carbon to halogen atom, and then we have here our hydrogen. Let me here, this is backside here, and then lines in this way. Now our nucleophile, let me write here our nucleophile here. Now we know that the halogen atom is more electronegative than carbon atom. Because of that, they'll pull the bonding electron towards itself, creating the partially negative. Now here, in this mechanism, our nucleophile attacks the partially positive carbon atom in a direction partially attached to. It attacks the partially positive carbon atom attached to the halogen atom from a direction opposite, that means in the direction opposite to the carbon to halogen bond. Now if this attacks our partially positive carbon atom, the electron will shift here from a direction opposite. When it attacks from a direction opposite to the carbon to halogen bond, it leads to the formation of a transition state. Now here, from here to here, it is a very slow state, and it leads to the formation of a transition. The nucleophile is attached. Our carbon to halogen bond is here. Our hydrogen is here. This is the transition state. It leads to the formation of a transition state. Now, in this state, the carbon atom is simultaneously bonded to the nucleophile, to our incoming nucleophile, as well as the leaving group, that is our halogen atom. Now, as the reaction proceeds, the carbon to nucleophile bond starts to form, and then the carbon to the leaving group, that means the carbon to the halogen bond, starts to weaken. Now, as this happens, the configuration of the carbon atom undergoes inversion. That means undergoes inversion like that of an inverted umbrella, and then here in that state, all the three carbon atoms are in the same plane. Here it is a planar structure, diagonal bipyramidal structure, and they are all in the same plane, and the attacking nucleophile and the leaving group, it is partially attached to the carbon atom. Now, as the attacking nucleophile approaches closer and closer to our carbon atom, the three carbon to hydrogen atoms keep on moving in the same direction till the attacking nucleophile attaches strongly to the carbon atom, and the leaving group leaves out from the carbon atom, As a result, we get an inverted configuration, and our product here will be, our reaction here is, remember, it is a very fast reaction. Therefore, the nucleophile is attached to the carbon atom, and then our hydrogen atom is here. Our H is here, and then we have here our X minus. The leaving group has already left the carbon atom. Therefore, in this way, we get, as a result, we get a inverted configuration. Now, during the formation of this transition state, the nucleophile approaches the carbon atom bearing the leaving group. Therefore, the presence of a bulky substituent here. The nucleophile is attacking our partially positive carbon atom. Therefore, the presence of a bulky substituent on or near the carbon atom will slow down the reaction, our reaction. And therefore, as a result, the reactivity in haloalkanes for SN2 mechanism will follow the order, that is our CH3X. The halogen will be more reactive than our primary haloalkane, then our secondary haloalkane, and then the least reactive one will be our tertiary haloalkane. Now, this is because the attacking nucleophile has to attack the carbon in an opposite direction. Therefore, the presence of bulky group or substituent on or near this carbon atom will slow down the reaction. As a result, the haloalkane having a smaller group will be more reactive. Therefore, we have our methyl group here. Therefore, this will be more reactive than primary, then secondary, then tertiary. When we compare the reactivity between primary, secondary, and tertiary haloalkanes, we will notice that the primary is more reactive, then secondary, then tertiary. Now, and here the reaction follows a second order kinetics. That is, the rate of the reaction depends on the concentration of both the reactants. That means in the first step itself, the nucleophile as well as the nucleophile as well as the haloalkane, they undergo the first step, and the reaction is a very slow step, and the rate of a reaction is determined by the slowest step. Therefore, we see here that it is a second order reaction. That is, the rate of the reaction depends on the concentration of both the reactants. Therefore, it is known as SN2 or bimolecular nucleophilic substitution reaction. Therefore, this is the mechanism of our nucleophilic substitution reaction for SN2 mechanism. Now, let's move on to the second mechanism, that is our substitution nucleophilic unimolecular reaction, or SN1 mechanism. Now, in this mechanism, the reaction proceeds through the heterolite cleavage of the carbon to halogen bond, leading to the formation of a carbocation and a halide ion in the first step. Here, we will see that our SN1 reaction is facilitated by polar protic solvents such as water, alcohol, etc., and it occurs in two steps. Here we see here that our SN1 mechanism occurs only in one step. Remember, the transition state is just a temporary state. It occurs very quickly. It's a matter of seconds. That because of this, we see here that our SN2 mechanism occurs only in one step. Now here, our SN1 mechanism occurs in two steps. Now here, in the first step, a tertiary carbocation is formed. Now, so here, if we have our carbon to halogen atom, here the first step 1 is a very slow step. Therefore, we'll be here. It results, remember we have to generate a tertiary carbocation. Why are we generating a tertiary carbocation? It's because we know that a tertiary carbocation is more. The greater the stability of the carbocation, greater will be the ease of its formation, of the product from the haloalkane, and faster will be the rate of the reaction. Therefore, in this case, the tertiary haloalkanes undergo SN1 mechanism at a faster rate because of the high stability of our tertiary carbocation. This is the first step. Now in the second step, it involves the nucleophilic attack on the carbocation. If this is our carbocation, we have our carbocation here, our tertiary carbocation here. If we take OH ion hydroxide, the reaction here is very fast. Therefore, we'll be getting here a tertiary alcohol here. Therefore, we see here that in SN1 mechanism, the reaction follows first order kinetics. That is, the rate of the reaction depends on the concentration of only one reactant, that is our tertiary haloalkane. Why? Because the rate of the reaction depends on the slowest step, and we know that in the slowest step we have only one concentration term, that is, we have only one reactant. Therefore, the reaction follows a first order kinetics, and thus the rate of the reaction depends on the concentration of only our tertiary haloalkane. Now in SN1 mechanism, the order of the reactivity will be such that a tertiary haloalkane will be more reactive, then secondary, then primary. This is just the opposite of our SN2 bimolecular nucleophilic substitution reaction. Therefore, this is the two different nucleophilic substitution reactions that happens in haloalkanes. That is, the first one is SN2 bimolecular substitution reaction, and the second one is SN1 unimolecular nucleophilic substitution reaction. Here it occurs only in one step, and here it follows a second order kinetics because the rate of the reaction depends on the concentration of both the nucleophile and the alkyl halide, whereas in our SN1 mechanism, the rate of the reaction will depend on the concentration term of only our tertiary haloalkanes. Therefore, this is the explanation on the mechanism of nucleophilic substitution reaction in haloalkanes.